ask a question. In the problem you just did, particle's going like this. All right. What's the direction of the angular momentum about this point? All right. So the problem asks for the direction of the angular velocity at the end, and that's the same direction as the angular momentum. So what's the direction? Is it in some direction in the plane? Yes or no? Into the blackboard. How do you get that? You use the right-hand rule. What is my R? All right, so we have an R like that. I take, and then I have this V. And so I have R down, crossed into V, into the blackboard, into the page, or some of you use the K vector, it would be minus K. All right? So that's what we mean when we say direction. But before we get into that, I'll just redo a demonstration that we did on Monday just to make it a little more dramatic, because we happen to have some weights to do it. All right. Now, I can either ask for a volunteer, or I could do it myself. What would you prefer? I guess I'll do it. I'll need your help, though. So I'm going to get on there. You're going to have to hold me so I don't fall. So you turn me just a little bit. Whoa, that is fast. All right. So that was very fast. Now, turn me a little bit. See, that's not so bad. All right. Why did I stop, do you think? Friction. Let's just do the friction. And I can even feel what I did was, when I stopped, I kind of, one foot went down on one end, and that kind of put a lot more friction on the axle. So that's what happened. So I was turning like this, right? Which way is the angular momentum? Up, right? You let your hand go the way I'm turning, and the thumb points in the direction of the angular momentum. All right, so here's a nifty thing. So I have a bicycle wheel here, and it's pretty, you know, it's kind of floppy there. But if I rotate it and stick it on there, it's actually pretty steady. I even touched it and it stayed there. Okay? So it's, when something has angular momentum, it takes some extra torque. It takes some torque to stop it. All right, so I'm going to tell you a story. This was a demo done by not my professor, but I was a teaching assistant at Cornell. And at the beginning of class, there was a suitcase sitting at the end of the hallway. It was a big hall like this, maybe even bigger. The professor picked up this suitcase. It was pretty heavy, but he picked it up, and he walked to the end of the lecture hall, and he put it down. And then he went on with his lecture. And then a little bit later, he asked the student to go get the suitcase. He needed the suitcase. So the student, not knowing any better, went like this. He picked up the suitcase, and then he tried to turn it so that he could bring it back. And he couldn't do it. He couldn't turn the suitcase. What do you think was going on? Unbeknownst to the students, before the suitcase was even touched, they had put a wheel, a very massive wheel, a disc, connected inside the suitcase with a huge wheel, very massive wheel, that was spun at a very high rate. All right? And there was essentially no friction on the axle of this disk that was turning around. So it had a huge angular momentum. And it was silent. Couldn't hear it. Nobody could hear anything. And so in order to turn the suitcase, you had to exert a torque. All right? Because we know, this is what we learned last time, that the torque is equal to dL dt. All right? And if L is a vector, turning the suitcase means you're changing L. You're changing the direction of L. The torque needed to do it was too much. The student's wrist wasn't strong enough to do this. He couldn't even do that, not even a little bit, because there was so much angular momentum in that suitcase. So we're going to use this idea today to see how tops work, spinning tops work. We're not going to do any calculations. It's too complicated, too involved. But we should be able to understand the idea. So we're going to start with this thing here. All right, so I spin it. I'm spinning it around like this. Which way is the angular momentum? Down. Okay. I want to spin it the other way so that the angular momentum is up. All right, so the angular momentum is up. Now, this is not like a real top because it has a flat pivot here. All right, so it's very stuck in its one direction, and it can easily just point straight up. If you had a real top, what would happen is you would have it at an angle like this a little bit. And I can't really keep it at an angle. It just kind of moves around. But let's see if we can figure out what it'll do if the top was at an angle like that. All right? Because it's impossible if the pivot is a point to make it go straight up. That's very difficult. All right, so what do you think is going to happen? So the way we figure this out is we have to draw a diagram. This is the top. Here's the pivot down here. And let's say it's rotating like this. Which way is L? Is it straight up? Is it? No, which way is it? It's at an angle. It's like this, right? So that's L. Okay? Where is the center of mass of this top, roughly? Somebody pointed out to me where the center of mass is. So the center of mass is somewhere around there. All right, so we'll call that center mass. What are the forces on the top? Normal, did you say? Normal. All right. Where is the normal force? Where does it act? Up here? Now hold on a second. We want a force on the top. Forces are either gravity or where the top is touching something. That's the only places you can have forces. What is touching the top? Touching. So the floor is touching the top. So there's a force right there. What direction is that force? Is it up, down, sideways? What is it? Up. Okay, so it might be up. So there's a force up there. So that's one force. Where does gravity act? There, right? Which way is that force? The gravitational force is down, right? Gravity is down. Okay, so we have that. Are there any other forces? So there could be friction acting over here, right? Right, so maybe some kind of friction. I'm not even sure what direction it would be. All right. So now we want to calculate the torque on the top. But in order to calculate the torque, we have to choose an axis of rotation or a location on this where we're taking the torque about. Any ideas what axis or what point we should use? All right, I'm going to draw 3 points. That's 1 point. That's another point. And that's a third point, C. All right, so there's 3 points. Should I use A? How many say yes? How many say no? All right, should I choose B? How many say yes? How many say no? All right, what about C? No. All right, you could choose any one you want. Why do we choose B? B doesn't move. That's a good reason. Yeah, that's good. So that makes life easier. B doesn't move. All right? So that's one reason we can choose B. Another reason for choosing B. Any other reason? The point is there are a lot of forces at the pivot point that we don't know much about. And what is the torque due to this normal force at that point? It's 0 because the moment arm is 0. So it's good not to use that. It's good to use that point because that way we don't have to worry about all these other forces. We don't have to worry about friction. We don't have to worry about the normal force because the torque due to them is 0. What's the torque due to gravity? So we're doing the torque about this point. So we draw a vector r like that, right? The r vector goes from the axis to the point of application of the force. Is that correct? So it's from there to there. So which way is the torque? Up, down, into, out of the blackboard, left, right? What is it? Out of the blackboard. How you get that is R cross F is this way. So that means there's a torque out of the blackboard. Right? So let's write that down. Tau out of blackboard, even though it's not black. But nobody calls it a green board. Okay. So there's a torque out of the blackboard. So what is that going to do? What does the torque do? It's going to make it rotate with an angular momentum or angular velocity or angular acceleration in the same way as the torque. So the torque is out of the blackboard. So it's like this, right? How is this thing going to rotate? So remember, it might be better to look at it at a 3D version. So we have it like that. All right? So R coming up there. Gravity is down. So if it was, let's say it was like this. Is it that way? What is it? That way? All right, so the torque is that way. So what is this thing going to do? What is the change in L? That's what we got to look at. So the torque is going to give you a change in L. So the change in L is out this way, right? The change in L is out this way. Is that right? Torque is out, change in L out this way. So this implies change in L is out of blackboard. All right? So the change in L is out of the blackboard. So what is it? If delta L is out this way, so the new L is going to have the same magnitude as the old one, but a different direction. So instead of being like this, how's it going to be? It's going to be a little bit like this, right? All right? So instead of pointing like this, how's it going to point? Instead of pointing like that, what is it going to do? Point like that? Is that what it's going to do? So it's going like that. It's going to point like that. How's it going to do that? Well, the way it does that is it's like that. It's going to go around like that. See that? See, right now, L is like that. Make it more dramatic. And then L, instead of pointing like that, it's going to point over there, right? Is that right? So in order to get over there, it's got to turn like that. Everybody see that? So we get L, points like that. So what happens to this thing is that and you've seen it, anyone who's seen a top rotate. Let's say this is the top. It's spinning on its axis. It's going to go around like this. Okay? So the magnitude of L does not change, only its direction. All right? And this motion is called precession. That's called precession. Is that correct? Yeah. So that motion is precession. Right? And every top will do that because it's virtually impossible to keep it straight up. But that's not even the whole story. Because if you look at this thing, it's spinning, and now it's going around like this, right? It's at a certain angular momentum, right? And to keep going like this, it has to have the right angular momentum. And so it might slip down a little bit. It might go down a little bit, right? Either due to friction or some other reason. So if it's going down, it has its angular momentum in this direction has changed a little. And so there'll be a torque causing it to go back up. And so what actually happens is it goes around like this, and then it also goes up and down like that. All right? And that's how it goes. So in other words, you have, this is my top, so it goes around this axis like this, and it also goes up and down like this. Okay? Sometimes it's rotating too slowly, so it might fall, right? Because when the top rotates slowly, it falls. So it falls, okay? The torque then is in the other direction, so it moves up a little bit, and then it goes too past that point, it's too fast, and it comes back and forth, back and forth. And so if you watch the motion, you get a motion back and forth like this as it's going around. All right, that motion is called nutation. All right, okay. So here's a spinning top. It's a little easier to see what's going on in this configuration. An angular momentum about 3 axes to start with. One is about this axis, so it's going to precess. One is about the x-axis, like this. And then this thing is spinning. It's spinning, so it has a certain spin. So let's just watch what happens. So if this is spinning like this, and then we have a force down due to gravity at about this axis, and R is this way, so R cross F. Is that right? No, F is that way. R is from here to here, so it should go around in a circle. depending on the way you may have the view wrong. All right. So what it's showing you is how it's moving. Oh, I guess it started out a little bit the other way. So notice how the top is going around like this, and it's also going up and down. So the up and down motion, this motion is called nutation, and this motion going around the axis is called precession. So if we have all the forces right, it's doing it in the right direction. Delta L is going that way. When it was, so right, let me stop it. So here's the original L. Due to the spinning, gravity is down, R is this way, about that, right? So R cross F, there's an L that way. So it's changing L. They may have had it go the wrong way, I don't know. But the spinning could be presumably, maybe it's going like that, and because of that, it's rotating the other way. Okay? All right. But you can see the motion is going around precession and then also along there. So strain, they might have the coordinates slightly off. All right? But the basic idea that it rotates, it spins, it rotates, it precesses, and then it goes up and down. All right? So we can see, watch that. So do it. Going around and around as it goes around. All right, so that's the idea of precession and nutation. And there's no way in the world that you can really explain this without thinking of angular momentum as a vector and torque as a vector, and trying to figure out what the change in direction is. Also, notice the following important point. The torque on the spinning object does not change the spin, because all the torques on that object are perpendicular to the angular momentum due to the spin. So if the change in L is perpendicular to L, all that does is change the direction of L. Just like if the acceleration is perpendicular to the velocity, it does not change the speed of the object. It just changes its direction. It can make it go around in a circle. Okay? So that's what we have here. I know this is confusing, and anything I do or say will not make it less confusing. The only way for you to do it is to really do it on your own. Is think about it, draw pictures, draw diagrams, draw all the vectors, and see if it's doing what you think it's doing. And you could use, in the textbook, there are a couple of figures that you can use to help you. Okay? Let's try this. All right? All right, so there it is. See, it's going around in a circle. All right? And if I don't know if I can tip it at all. Yeah, it's hard to show that. There's a little bit of nutation. Let me see if I can see it. Yeah, if you look carefully, the rim goes a little closer to the wire and a little further away. But here it is. It's just processing around. Okay? So that's good. So, which way is it turning? Like this? I can't remember which way it's turning. Anyone remember? This way? So it's going, so it's like this. So, whoops. Like that? The other way, like that? So L is like that? All right. So L is towards the string. Is that right? All right, L is towards the string. All right, so which way is the torque on this? Which way is the torque? Oops. Oh, now it's really nutating for a while there. There it goes. So which way is the torque? So there's the gravity is down, right? And R is, let's say we're right there, right? So the gravity is straight down. R is over that way. So R cross F is which way? Like right here. Is it towards you or away from you? Towards you. All right, so the delta L is towards you. So it was originally going like that. The delta L is that way, so now it's going like that. So it has to move up like that. Right? Is that right? I think like it has to be there originally, and now it has to move like that. So that way it'll go that way. Okay? So that's the idea. So you can play with any objects you have and think about how it goes. It's not easy, but you can do it. All right. That's a nice picture. It's the one subject that very few physicists can do in their head. You know, can just figure out from scratch because there's so many things to consider. So many angles, so many reference frames, etc. There are 3 forces on this meter stick. All right, what are those 3? There's gravity, normal force. What normal force? Due to my finger, there's one here, right? Are they the same? No, not necessarily the same. So if I just look at forces, all I can say is that the sum of the normal forces is equal to mg, right? That's all I can. But presumably, I can figure out what each normal force is. And the only way to do that is to use torque. So I can look at the torque about the middle, and so I'd say the normal force this way times the moment arm. So let's say this is at 80, and I'm going to put this at 40. Okay? So n times 30, because 80 minus 50 is 30. The n over here must equal the n over here times 10, because it's at 40. So which n is bigger? This finger or this finger? The left finger. This is my left? Yeah. All right. So you can really see this. If I put this real close and very far away, I can feel the difference. Right? Let's see if you can feel it. Put your finger very close. Let's put it as close and the other one there. Does this feel heavier? Yes. All right. The other important thing about that is she feeling the weight on her fingers? What is she feeling on her fingers? Is it the weight? Does she sense gravity? No, she is feeling the normal force. You're feeling the normal force on your finger. Because your finger is exerting a normal force up. Therefore, the meter stick exerting a normal force down on your finger. It's not exerting a gravitational force on your finger. The gravitational force on your finger due to this meter stick is so tiny that you could never sense it. Just like the force I exert on you is incredibly tiny. Like you're not moving towards me because of my gravitational force. No matter how attractive I am, you're not doing that, okay? All right, so the gravitational force due to small objects is negligible. It's only the gravitational force due to you. All right, so we now have this basic idea. If an object, an extended object, does not move, we call that static equilibrium. So object doesn't move. All right? And there are two conditions. The sum of all the forces equals 0, and the sum of all the torques equals 0. Both are needed. And the beauty of the torque thing is that is true, the sum of the torques about any axis you choose has to be 0. So you can choose whatever axis is useful for you. Not so bad. Still works. Doesn't work. So presumably there's some location, some angle at which this ruler will fall. Let's figure out what that angle is. In this example here, which surface do you think is slippier? Any ideas, or are they about the same? Is this slippier than this? What do you think? We could do this one. Watch this. And we have that. Is there more friction on here or down there? Which one? Here. Okay, so let's do that situation. So we'll say the coefficient, so we're going to draw situation. Here's the wall. Here's the meter stick. Okay? And we'll have a static friction here, mu sub s, and we'll let this one be, let's say, 2 mu sub s. Okay, so the friction up there is greater. All right? Okay. And this has a weight, W. That means W equals mg. All right? And this has a length, L equals 1.0 meters. All right? Everybody agree? Yeah. All right? We want to find out what angle this is. All right? Such that it'll work. So it's in static equilibrium. So we want to find the maximum angle. We'll assume there's a maximum force here and a maximum force there. All right? That way we can use, what does that allow us to use? Why do I want the maximum? Because obviously it can be there many places. I want the maximum so that I can use the formula that friction is mu times the normal force. All right, so let's find the sum of the forces and the sum of the torques. All right, where does W act? Where? At the center. So we have a W here. All right, then we have forces here. What do we have? We have a normal. We'll call this normal, what's this? The wall. And then we have friction. Which way is friction, up or down? It's up. Why? Why is friction up? It's up because this is trying to go down, right? So the force is up. What about here? We have a normal force due to the floor, okay? And what about friction? Which way is friction? To the left or to the right? Left. Yeah, because it's trying to do that. All right, so we'll call that F floor. All right, now let's use Newton's second law. All right, the sum of the forces in the x direction, we have NW equals what? Yeah, NW equals FF, right? So we have NW minus that has to equal 0. Is that it? That's it. All right, in the y direction, what do we have? We have N floor plus F wall minus W equals 0, right? Okay, so far so good. Now, unfortunately, we have 1. You might think we have 1, 2 unknowns. We can maybe get rid of them by putting in those coefficients of friction. But I'm going to just do it forgetting about them for the moment. All right? And let's choose a torque. Where do you want to choose the torque about? There are 3 obvious choices. Here, here, here. The bottom? All right. Let's do the bottom. So we want the torque about here. Okay? So we have W times L over 2 times, is it the cosine of theta or the sine of theta? So it's L over 2, but it's not W times L over 2. Is it a cosine theta or the sine of theta? Cosine theta. You say cosine theta. Everybody agree? So theta is 90 degrees straight up. There's no torque, right? Because W and R are parallel. Where theta is 0, down here. So it's down there. So R would be this way, W that way, so we'd have a torque. Is that right? Now, is it positive or negative? We call positive what? Clockwise or counterclockwise? Counterclockwise? Counterclockwise. So this is trying to, this force here, is it trying to make it go this way or this way? So it's counterclockwise, so it's positive. So this is, we're doing this about here. Call that A, tau A. All right. And what's the torque do to these guys? Well, we have the friction force, F wall. It's also cosine theta, but now it's times L, right? And is it cosine theta still? Yeah, still cosine theta. Is it positive or negative? It's got to be negative, right? Because this force is up, this force is down, and both the R's are in the same direction. What about the wall force? This force. So that's NW times L again. But this time it's what? Sine theta? Is that right? Sine theta? And it's a positive or negative? Positive or negative? Is this force trying to make it go clockwise or counterclockwise? This force here. What is it doing? Is that clockwise or counterclockwise? It's clockwise, so that's minus, right? All right, so that has to equal 0. All right, so we're got all that. So from this, we can get what the tan of theta is. It'll be W L over 2 minus FL divided by NW times L. So interestingly enough, the L's cancel. So we have W over 2. Which F is this? FW. So what we'd have to do is find expressions for this and this. All right, so maybe we could write this is, what would this be? US times what? N floor, right? And this guy would be 2 mu s times N wall. I don't know if that would help us. All right, so we'd have to go through all this and see if we can get rid of these two in terms of W. Let's see, can we do that? Let's see if we can do that. Here we have wall and F, FW and NF. So it's NW and NF. Yeah, and then NW and NF. So I think we could do it. Let's say NF. Let's see, how do you want to do this? So this equation is NF plus FW where FW is 2 mu s NW equals W, right? And then we could get rid of one of these. NF is NW over NS, right? So this is, what is that? That's NW over mu s. All right? So then I can say NW is equal to W divided by 1 over mu s plus 2 mu s. All right? So I have NW. And then FW is just this. So I can put that in. And presumably I could get the answer. It's probably not that interesting. But I can find an angle.